So yeah, it's great to be here. Thanks for staying here late. A quick intro. I'm gonna do an initial introduction to what we're building and what kind of applications we're targeting, and then Fred is gonna do a deeper dive on how the network actually works. But before we get started, I think Sergey started great. He mentioned how data inputs to smart contracts is a big problem in this space. We're focused on the problem of privacy. And to give you some background, Enigma started as a research project out of MIT in 2015, and what we realized quickly was decentralization is a great promise. Blockchains are an amazing innovation. However, blockchains alone cannot fully fulfill the promise of decentralization, and that's primarily due to the fact that the data on blockchains are visible to everyone, right? You can't put anything sensitive there. So what we're doing is we're saying we're building the privacy layer for the decentralized web, and we're making blockchains fit to handle sensitive data for the first time. The way we do that is we build a privacy protocol where computations can take place on encrypted data. And we introduce this concept of secret contracts. A secret contract is similar to a smart contract. The difference is the data inputs are not visible to the network. So you can call a contract with certain inputs. The inputs go to the network. Certain nodes or call workers are selected at random. They're able to compute and reach a consensus without anyone seeing what the data inputs were. And there are two ways in which we do this. Our research has been based on multi-party computation, which is a purely cryptographic method, software-based cryptography. However, it has significant performance limitations. Similar to Chainlink, we're working with Intel SGX for now. Since this topic has been hotly debated, we have ways in which we can reduce trust in SGX, and I think it's important to mention them. So one thing we do is, Fred will go into this in more detail, but we have a way in which nodes rotate while working on a contract. So even if a node is, let's say, compromised, the time at which this attack can happen is very, very little. We can see who has been compromised because of the consensus process, and then finally merging this with the MPC research, we can actually have different SGX devices work on a random piece of the data, which means even if the SGXs are compromised, you cannot make anything of the data. This last part is at least a year out, but we think that's a great way to reduce the dependencies there. And then eventually we want to launch a new version of the network where if you want, you can run contracts entirely based on MPC. So what do we do with this? There are a couple of applications that we are working with. One is around governance. This is where we get the most traction, and this is what we're collaborating with Ocean on. The problem with voting is if your votes are public on a smart contract ecosystem, bribery can become contractual. So if I know which way you're going to vote at some point, I can put money on a contract and say, if you vote this way, I'm going to pay you. So we can solve that problem when you keep your votes secret. Another thing that this does is, right now, a lot of voting applications do pre-tally privacy by doing this concept of commit reveals, which means you first commit the hash of your vote, and at the future time you reveal it, and people forget to do the second transaction, and it's usually a nightmare. So while we started this journey just focusing on data privacy, we realized that this also helps with usability of blockchains, which I think is a big part. Another thing that we're very focused on is around auctions. Currently, you cannot do sealed bid auctions. What we have, you can put in encrypted bits, and if you think about a two-sided auction, that becomes an order book. So you can build things like privacy-preserving decentralized exchanges. You can build things like dark pools, where the orders and the post-settlement privacy is maintained. And I think that's a big need in this ecosystem. So you can basically replicate a centralized exchange in a decentralized way. And without going into too much detail, another area that we're interested, or I'm interested a lot in, is this identity part. I think we have a lot of data that we create on Web 2.0, whether that's your Facebook traffic or like what you purchase on Amazon, whatnot. With things like GDPR, we're given the promise that we can finally use those things. And to us, it's interesting how you can use that data that you create on Web 2.0 in a useful way in smart contracts. That's kind of like relevant to what Sergey also mentioned. But on that, we're working with this company out of Berlin called Data Wallet. What they do is they take your Facebook data and they essentially run algorithms on it to determine whether you're an actual legitimate human being or a bot. And what we're doing with them is, instead of running their algorithm centrally on their servers, they can load that, they can put that algorithm in our network as a secret contract. And as a user, you can send in your Facebook data encrypted, have some computation take place there, nodes reach a consensus, and we can create an ERC 725 for you that can enable you to participate in airdrops, ICOs, if there are any left, and also things like just like anything that you need civil prevention, games, investment opportunities, whatnot. So that's kind of what we do. Super excited to be hosted by Ocean. Feng is working with us there. Hopefully we'll be able to have something to demo soon. And with that, I'm going to pass it to Fred to talk about this, like this data wallet example we had, and then just go a bit deeper into the network.
Okay. Hi, my name is Frederic. I'm an engineer here for Enigma. So this sequence diagram, I'm just going to go over quickly. This is probably very naively represented. I think this use case isn't completely built, but the idea is to sort of explain how the architecture of our network operates. And so I'm gonna explain it functionally here, and then we're gonna explain it component by component in the next slide. So essentially in this, is there a pointer on this? Okay, so in this sequence diagram, the idea is that there is a DApp, which here is for this particular scenario is the data wallet DApp that will invoke our Enigma network and submit a task. So we call a computation a task. So essentially a task for the Enigma network is kind of the equivalent of a transaction on Ethereum. So the data wallet app will submit a task to the network and essentially receive some results. So to explain how it works more specifically, the data wallet app will request some user data from Facebook, do some magic there. I don't know exactly how they sort of process the data that they receive from Facebook, but they get some data from Facebook. Then they would create a task for the Enigma network. And to create a task, basically, what they have to do is to call a function of a secret contract. And I'll explain in the next slide a little bit what a secret contract is in more details. But as the name might suggest, a secret contract is analogous to an Ethereum smart contract, but it's privacy preserving, so we called it a secret contract. We use slightly different runtime environment. We use WASM, and there are some variations, but essentially, like, we have our own smart contract engine that we call secret contracts. So essentially, to submit a task, you have to call a function of a predefined secret contract, and you have to submit some inputs. So in this case, the data wallet app packages some data that it got from Facebook. These are the inputs of the function of the secret contract that are being submitted. And this shows an interesting characteristics of our network is that we are sort of a side chain to Ethereum, but we're not fully a blockchain in the sense that we don't have a ledger. So basically we use Ethereum for consensus. So essentially we have a series of nodes that work together to execute these computations in a specific way that I would show later. But we use Ethereum for consensus. We could use other things for consensus. So for example, we could use a parity, parachain for consensus or anything like that. But basically, at this point, we're trying to be very friendly and interoperable with Ethereum in such a way that we can do things like transfer ERC20 tokens, like use ERC20 tokens in our secret contracts without having to do a deposit a priori and some other complexity there. Okay, so back to the flowchart. So the way it works is that in order to create a task, you have to submit some data to Ethereum. So basically create a transaction on Ethereum. And what this transaction is that it's a transaction that stores a hash of all of the inputs of the task. So the task has multiple inputs, the function name, perhaps the bytecode of the secret contract, the arguments. So from that, the dApp creates a hash and submits that to Ethereum. And then the dApp submits the actual inputs into the Enigma network. The dApp will connect to the Enigma network just like it connects to Ethereum. Basically, it connects to one node of the network, and then that node will sort of dispatch the task. We use libp2p for the communication between nodes, and we also use it for storage. So we have a kind of our own local IPFS type of storage inside of our network. So essentially, we create the transaction on Ethereum with the hash, we submit the input to a node of Enigma, and then by a process that I will explain in the next slide, a group of, we call them workers, so a group of nodes will pick up the task and essentially decrypt the input and recreate the state of the secret contract, because our secret contracts, like Ethereum smart contracts, have a state. Ours are a bit more complicated because the state is encrypted. So the workers that are running this computation will recreate the state of the contract, decrypt the input, run the computation, and then return the results. Now, when a computation task is executed, there are essentially three types of outputs that are created. First output is if the function has a return statement, then obviously the results of this return statement are being returned to the end user. So basically, the dApp will receive the results of the function that it called. Whatever comes from the return statement is being returned to them via the network and so forth. The second type of output might be side effects on the state of this contract, of this secret contract. So just like Ethereum, this bot or not function might want to save things in the state of the secret contract, and it can do that. So it's sort of the second type of input, and this is managed directly. It's not returned by the user, but rather it's committed in this certain specific way that I'll go over in the next slide. And the third type of input, which is relevant in this diagram, and this is optional, but certain functions of a secret contract might have side effects on Ethereum. So we're allowing a sort of a bridge to Ethereum where from a function of an Enigma secret contract, you may call a function of an Ethereum smart contract. And this is useful for something like this, where we're getting these private inputs, information that we don't want to have public. We are reducing this data, essentially, producing an aggregate, and the aggregate itself, in this flowchart, we're committing that to an Ethereum smart contract so that it's available publicly. So we just computed this information, created an aggregate, put this aggregate on a public registry, so that the next time that we want to check if user address, ABCD0X, whatever, is a bot, then we already have this information stored in a registry on Ethereum, which is available publicly. We don't have the private data anywhere, but we have the result, which is stored on Ethereum.
I think one thing that's very interesting is there's not been close to production level systems for general purpose compute with secret states. And that's like something that's very exciting for us. And also, please give us 5 minutes because we haven't really timed this, so we don't want to just go for too long. Yeah.
Yes, that's true. I don't mean to ramble there. Okay, so going to do this a little bit faster. So I mean, this is a bit technical. So I'm going to go fast, and then if you guys have questions, then I'll answer them. But this is kind of how the network is structured. Essentially, we have the secret contract, which I kind of explained how it worked earlier, and we have this concept of epoch. So essentially, the way it works is that for each epoch, which is an epoch is essentially like just time. It's a number we calculated by using a number of blocks on Ethereum. So after X blocks on Ethereum, an epoch ends. And what we do when an epoch ends is that we select a new group of workers to work on each of the secret contracts that are deployed on the network. So we use randomness for this, and we also use the stake that the workers have deposited. So we have an incentive model here, which requires each node that want to register as a worker to deposit some tokens, and of course we use our token ENG for that. So each node will deposit an amount of token, and depending on how much token they've deposited, that will affect their likelihood of ever being selected as a worker for a contract. And the reason why we rotate the worker every epoch is manifold. Like, there are some security implications, but we also want to be able to distribute the reward more equally, because some of the secret contract might see very little usage, while some might see a lot of usage. So we want to give a chance to every worker to be, part of any number of contracts, essentially, like distribute the kind of workload that they might receive.
And this is like similar to like a contract level sharding.
Right. Okay. So then this is kind of summarizing again, like giving a different view of what I just explained about how a task flows in the system. So essentially, a DApp user, which in our example earlier was the data wallet thing, would submit a task to the network. So essentially, it will first submit a task to the Ethereum network, which would then go to the Enigma network. So essentially, the task record here is the task record that's first submitted to the Ethereum network, which contains the hash of all of the input, because remember, we use Ethereum as our final consensus. So Ethereum is kind of the source of truth. So we first create that record on Ethereum, which contains a hash of all of the inputs. Then number two, we send the computation to the Enigma network. Then a worker is selected, because we're in a given epoch and there's a group of workers that have been selected for that epoch. The workers compute the task, and then we also have the notion of a batch, which we do for basically performance. So essentially, the way it works is that if I'm a DApp user and I send multiple tasks for a given contract, or even multiple DApp users sending multiple tasks for a given contract, and these tasks don't have side effects on Ethereum, essentially their tasks are self-contained in the sense that, they're calculating something where the DApp user who sent it just wants the results, then we don't have to commit those to we don't have to commit anything to Ethereum every time. So basically what we do is we batch them locally, and we commit them to Ethereum only under two conditions. One, when the epoch ends and we reshuffle the workers, or when there are side effects on Ethereum in the manner that I just mentioned, where, say, one of the tasks requires a call to an Ethereum function. So we're just trying, I guess the point here is that we're just trying to optimize how many commits we do on Ethereum to kind of optimize the performance. So like and our network is very fast because, again, as John mentioned, we use IntelliGX, which gives us some security assumptions that we don't have necessarily on a fully public on a network that uses like generic like hardware or where the hardware doesn't have any kind of property that we can control that can guarantee any security. So we can use, basically the point is we can use a smaller number of nodes essentially executing each computations. So we can execute computations like very fast because of that, because we have like only a small number of nodes that are assigned to each computations. So we can batch them, so we can execute many computations very fast. And what we commit on Ethereum when the commit triggers occur is we just simply commit, like, again, hashes. So we commit a hash of the results of that computation in addition to a proof that essentially shows that certain inputs have been used for the computation, so that the dApp user could go and verify the proof that's been committed on chain to make sure that the results that have been committed on chain originate from the inputs that the dApp user provided. And then we also commit a hash of the results. And also, again, we also rely on SGX for this because we also have a registration process by which each of these worker nodes first have to register to the network, and in order to do that, it undergoes a verification process to make sure that one, the worker has an authentic, SGX enclave that hasn't been tampered with, and also that it's running the Enigma code on that enclave. So essentially, the proof that we're committing has a number of guarantees to ensure that the computation was executed correctly, and that's what we call here a task receipt. Yeah, so that's about it here. Let's see if there's anything. I've already explained this. I've explained the batch.
How are we doing on time?
Yeah, if we don't have, I think if we're almost done, we could go with some questions if you want.
Yeah, we can end and take questions.
Yeah, okay.
Thank you. Please.
Contracts are encrypted in a multi-party setting?
No, right now the contracts are not encrypted at all, because if you encrypt the contract and the inputs, then you have no idea what's going on. So right now only the inputs are encrypted, and
why do you call them private contracts then?
Because you don't see the inputs.
Okay.
Yeah, we want the code to be auditable, but not the inputs that go through it. So.
But there are people, for example, take CryptoKitties, right? They release their code now. They're tens of versions of the CryptoKitties. So there are people who want their code to be private as well. It's something that's technically doable. We're not sure whether it's it makes sense, but to be seen. It's something possible if people need it.
It will require maybe a third-party audit process, perhaps, where the code would be audited, and then you would have to trust that the auditor has audited it and it has certain properties. I don't think we can just obfuscate the code, and because otherwise the code could contain a malware and no one would know.
Is there some idea of gas for secret contracts?
Yes, so you have to pay the network in ENG to run these contracts. And if you're a user right now, what you would do is you would just pay ETH, and then would obfuscate that, and then work with someone like Kyber to exchange and make sure you can pay the nodes who are working on the contract.
Yeah, and we use the same gas metering logic that Ethereum, or at least the WASM implementation that we're using, has, but the fee would be much low. The fee is much lower than the gas you would pay on Ethereum, just because we don't have the same computational overhead. So you would be able to run quite extensive computations on this at a fraction of the cost. We're actually looking for machine learning use cases and things at that level. So it's not just a privacy, there's a scalability benefit as well.
So I understand that the smart contract itself, the code, is openly visible.
Yep.
But the input is not. Is the repetition of the code, the number of executions visible?
What do you mean by that exactly? Yeah.
So if I run a business and I have a specific code, and let's say I charge the same amount of money for each execution, then it would be very interesting for my competitor to understand how many times it was executed.
Interesting.
You wouldn't know that because the receipts that we submit on chain, if I can go back here, the receipts that are publicly verifiable, they contain what we call a task ID, which is basically a hash of all of the inputs. Because it's a hash of all of the inputs, you wouldn't be able to distinguish the function name from that, or even the contract code from that. So you just know that you ran all of these tasks, but you wouldn't be able to differentiate whether you ran function A, function B, function C from all of these tasks.
But if I know how much it costs, is it indirectly possible to understand how many times it was executed?
That's a good point.
It comes from a certain account.
Yeah.
Like if I have an account there and it costs me, say, so and so many tokens to run a specific program, and the balance decreases by so and so much, that's a giveaway, isn't it?
That's a very interesting point, actually. It's something that we should, we need to think about this one more carefully.
But I have a question, so the way it happens is you interact with one contract on Ethereum and you put a deposit there, and every time something runs, basically something is deducted there. But there's one contract on Ethereum that maps to all the secret contracts on Enigma. So given that kind of randomness, can you still deduce that kind of information?
Possibly. Yeah, I think we need to think about that, because right now we are tracking the reward per task.
Okay.
So believe we can obfuscate the reward per task, but then we have to see what the side effects of that would be.
Okay.
Also, I would not call this randomness.
Okay. Thanks for correcting me.
Yeah.
So, any more questions? One last question? If not, John, Fred, thank you for
Thank you for having us, and thank you for staying late.